begin talking about the topics we'll be considering, and the main topic of discussion today is going to be on functions and function notation. We're going to define what a function is and also look at the different notation that's associated with it. And this is all at the beginning of chapter 1. Now, before I jump into this, a lot of students very frequently will ask, what is the prerequisite material for this course? I was looking around for, I'm going to be putting it in the textbook, but I just haven't had a chance. But there is a certain amount of algebra that you need. So let's take a look at the algebra prereq. And if you look, I'm going to show you, I placed something on our Blackboard site over here, so you can access that as well if you want to see what you should know. Let's go over that very briefly. So you can kind of look at what you really need to know as we're getting started over here. So if you come on to the Blackboard site over here, I put a new link, Algebra Review. You click on that link over here, or that tab, you get to this window, and here's an algebra review. I'm borrowing something from Stewart. We use actually the Stewart calculus book, so it's a reasonable review. There's 160 problems in here. I'm not doing, you can downplay a little bit with the binomial theorem. Not that it's not important, but in the grand scheme of things, it doesn't weigh as much importance as the other ones. But if you go in here, you can look at this. This is from Stewart's calculus, and it talks about the review of algebra. You could skip down to the actual problems and start going over the problems. Do you know how to do these problems? If you don't, you can go back and refer back to what's above this, and you have both the problems and the answers are posted here. So what I would do is I go through this, and do you know this material? This kind of takes the prerequisite algebra material of what you should know for this course. Now, if you don't and you can't figure it out, you can, I'll set aside a little bit of time from, to go over a couple of these questions from time to time. But this is the algebra that you really need to be comfortable with as we proceed in the pre-calculus portion of this. So I just want to kind of make that statement there before we kind of get started here, so everyone at least knows. So you may want to look at that, take a look at some of those problems. That'll tell you, are you ready to kind of do the pre-calculus? If not, then you need to practice that, because that's a big portion of what you will see. There's going to be a lot of algebraic manipulation and calculation, both in here as well as the calculus. Calculus is, a lot of that as well. So the more you practice it, the better off you'll be. Okay, so I just wanted to make that notice that I just kind of put that on the Blackboard site so you have access to that. Go through that, because we have a little bit of time now. We'll again until next Tuesday, because we're off on Monday. But you can take a look. I'm going to give you some homework for the functions and function notation, but in addition, you may want to review your algebra. Okay, so let's begin. From the algebra, as we recall way back in the algebra, the most fundamental object in algebra we dealt with were expressions. From algebra we had expressions, algebraic expressions. And we had various polynomial expressions, such as x squared plus, 2x minus 5, that's an expression. X minus 7, another expression. 2x plus 6 over x minus 2. Those were all expressions. Those are the fundamental building blocks of the algebra. And then when we went with expressions, what did you do? We learned how to set two expressions equal to each other. So you can then, from expressions, you get equations. And an equation is by setting two expressions equal to each other. For example, I could set x squared minus x is equal to, say, 2 or something like that. And that's an equation. And we would then go about and solve the equation by setting the expression x squared minus x equal to the expression 2. And then we learned how to solve equations. So you might say x squared minus x minus 2 is equal to 0. And we learned we could do things such as factoring. X minus 2 times x plus 1 is equal to 0. And we learned, okay, x equal to 2 and x equal to -1 are solutions, meaning they make this a true statement. This is all in single variables. So everyone knows how to do it. This is also some of the review problems that you'll see in this algebra review that I put on the website. Then we extended this to equations in 2 variables. So we went from equations in a single variable to equations in 2 variables. And then we looked at things such as y, that's one of the variables, is equal to 2x minus 3. Now, in this case, we couldn't solve for a single value that would make that a true statement. We found that there were infinitely many values that made that a true statement. And what did we do? Well, we used a Cartesian coordinate system. We introduced that idea and visually showed all the solutions to that equation in 2 variables. So we went to the Cartesian coordinate system. And then we were able to give a picture of that solution. Come over here. And it looks something like that. We learned how to do that graph. And the solutions of this were the sets of all those ordered pairs. So the solutions were nothing more than a set of ordered pairs, meaning we had an x value, a y value. Together, that gave us the ordered pair x comma y, which is a coordinate of the point. And you could put various ones in, 0, and then you got -3 out for that case. So that was my ordered pair, 0 comma -3, which is this point right there. You might have put in 1 over here. So you put in 1, you get 2 minus 3 is -1. That's another ordered pair. You could put in 2. So you get 4 minus 3, and you get 1, 2 comma 1. That gives you the other ordered pair. But again, we know we can't do them all, but that's what it would look like. It would be this point over here. You had the 1 point here, and then 2 comma 1 would be over here. And all of those ordered pairs were solutions to that equation in 2 variables. So that's going to be our starting point here. We're going to be looking at equations in 2 variables and looking at their solutions, which are illustrated here on that blue line, the graph of that blue line, and then try and extend that idea to something we're going to call a function. So the first thing we deal with is anytime we have some equation in 2 variables, there's a relationship between them. So we define something called a relation. And again, I'm going to point out to the fact that all of these solutions are related to these. Let me write it out specifically here. These are my ordered pairs. Okay. In general, we have what we call relation. And this is how we're going to define it. We're going to use our first definition over here. And here's our definition. It's a very basic definition. A relation is any set of ordered pairs. Now, there could be a finite number of them, or there could be an infinite number of them. So first you can get, for example, this is an example of a relation. It's a set. It's my set notation of ordered pairs. 1 comma 2. 1 comma 4. 2 comma 7. Minus 5 comma 3. That would define a relation. It's a finite relation. but it's a relation. I have an X and a Y, an ordered pair, and any set of ordered pairs. Anything I can write down as a relation. So that's a relation. And we can also look at the graphs. This is just listing a finite number, but a relation can also be illustrated both as a set of ordered pairs or as an infinite set of ordered pairs, which is its graph. So we can look at the graphs. Let me go online and show a few of those using Desmo. It's a nice little tool, just so you can get kind of used to seeing how to do all these various types of ordered pairs as equations. So here's our Desmos. Let's put in some relations over here. Here's another one we could put. We could say y squared is equal to 3x squared minus 4. So there it is. That's a relation. And it looks like that. Let's try another one. You have another relation with the x and y values. So you could have, y equal to 4x minus 3. There's another. Oh, not t. I want it to be y. Excuse me. Hitting the wrong thing. Got close, but missed it. There's another relation in blue. Here's another one. We could have y squared is equal to x or 3x minus 5 divided by 2x minus 7. That's another example of a relation. Well, here's another common one that you've seen before. Say y is equal to x squared minus 2x plus 1. And there we have right there the purple relation. So all of these are what we call relations. These have an infinite number, if you will, of ordered pairs that define them, as opposed to what I put on the board over there that only have a finite number. Okay, so we have relations. We'll go back now. And I know most of you have seen that. That's just a simple way of showing what a relation, any set of ordered pairs. Anything you can draw is a relation. What we're looking for is a special type of relation. A function is going to be a subset of relations. So a function has a very specific quality that we're looking for. So now another definition over here. So a function is a relation. So all functions are relations, but not all relations are functions. That's the first thing we're going to come across over here. Every function is, by definition, a relation. Not every relation is a function. Is a relation such that the x-coordinate of the ordered pair that defines that relation, of the set of ordered pairs that defines that relation, is, and this is a critical thing, not repeated. So you have no repeated x-coordinates. For example, this relation here I wrote here is not a function. Not a function. Why? Because notice this x-coordinate is repeated. So this relation is not a function. It would fail that test. That's going to be our primary simple definition. This is one of the basic ones. We can take other definitions, but this is the simplest way to do it. So if you can draw it, then we're going to look at the implications of this momentarily when we start looking at graphs. What does that imply for a graph? Let's kind of get a sense for it over here. Let's take a look at graphing those 4 points and see what we get. Take a little graph of those 4 points. So if I graph those 4 points, I have, 1 comma 2, 1 comma 4, and 2 comma 7, and minus 5 comma 3. Right about here. Now the fact that we cannot, this is a relation, but we're trying to exclude this problem right here. So we look at those 2 points and we can kind of see the issue right there. The problem we have with this that we would like to eliminate is ambiguity. Meaning, I'd like to know if I give my x coordinate, I'd like to know precisely where I'm going to go. But if I'm giving this x coordinate of 1, I don't know precisely where I'm going to go. I could go to the location y is equal to 2, or I could go to the location y is equal to 4. So it brings some ambiguity to things, and that's what the function concept would like to do. Remove that ambiguity. Meaning, if I think of this function as x and y, as x being an input and y being the output, that's another way of looking at this. And that's the way of reducing its ambiguity, if you will. But here's another way of looking at this notion, this idea of a function as an input and output. So this definition can be extended to think of this as, let the x coordinate be the input of the function. And the y coordinate be the output of the function. So what this is telling us is that for every input, I have only one output. And sometimes people draw a function machine over here. I have it in the textbook as well. You have some function machine. This is your function. And then you have something that goes in. The x goes in, and then something that comes out. Your y comes out. Feed in an x, you get one y out. You feed in the same x value, you're going to get the same y value that you had previously. So it doesn't change that. And you can take it out of the function machine based upon an input and an output. Now, what does this do graphically? Well, if I was to graph a function, I cannot have 2 values associated with a single input value. I can't have 2 outputs associated with an input value. So if I'm looking at graphs of functions, here's a graph, and if I was to graph it, again, my x is my input, my y, I'm going to treat that as my output. For every x, I can only have one y, so it has to kind of look something like this. One example of a function. Now, it could also look something like this. If I wanted to, it could look something like this. That's also an example of a function. Meaning, as I go along the x-axis, and I go over here, there's only one unique y that comes out for that one. There's only one unique y that comes out for this one. One unique y, which is right at the x value, was 0, excuse me, and then one unique y for that. These are examples of functions. These are not functions. So these are relations, but not functions. A relation doesn't have that restriction. We said any set of ordered pair, which ascribes itself to any graph that you can draw. So over here, this could be a relation. The problem with this, why it's not a function, is, for example, at this x value, I have that y, or that y. There's 3 possibilities. It gives ambiguity. So this relation is not a function. This kind of gives us a very simple geometric way of identifying functions from their graph, and we call that the vertical line test. So a function or a relation is a function if it passes what we call the vertical line test. So a relation is also a function if it passes something called the vertical line test, and I'll explain what that is. The vertical line test simply says if I draw a vertical line, I will only cross the graph of that function once. So if you draw a vertical line at any x value, the line only crosses the graph at most once. Crosses at most once. May not cross at all. Crosses the graph at most one time. So if I get rid of the, over here, we can just draw some vertical lines, if you will, and you can see which are functions and which are not. Since it only crosses that once, no more, that blue relation is also a function. This red relation is also a function. Now over here, it might not cross at all. Over here, it doesn't cross at all, so at most once. It doesn't have to cross. But for the blue one, it does cross once. The red one, it doesn't. Here, again, we have that problem. Here's a vertical line, and it crosses 3 times. This part's okay. It only crosses once. But as I move along here, I start seeing problems. Here I cross twice. Then I cross 3 times, etc. Get all those difficulties. So, graph of a function, graph of a relation. Now, this function is also a relation, but this relation is not a function. Okay, so we have that. Well, let's get a little more detailed now. Get down into the details of the x and the y's. This is where we get a little more mathematical. Okay. We're going to give special names to what we call the set of input values, the x coordinates, and the set of output values, or the y coordinates. So we call the set of all the input x values the domain of the function. That's a new terminology we can use. We can talk about something called the domain. The set of all the x values. And in a similar way, we call the set of all the output of the y values, output y values, the range of the function. So that's going to be very critical from here on out. Throughout the course, we're going to be trying to understand domains and ranges of the various types of functions. We're going to look at different classes of functions. We're going to look at algebraic functions. We're going to look at transcendental functions. We're going to look at all these different types of functions, and we're going to find what's their domain, what's their range. What can I put in, and what do I expect can come out? So let's kind of drill in on that domain and range, and let's take a look at some very simple functions. And now our focus is going to be on the domain and range, and how do we write that? Since these are going to be very critical definitions for us, so get comfortable with this. understanding what I can put in and what can come out. So here's some examples. Let's take a few graphical examples. I'll do it by a graph. You can also do it by sets of points. There are some problems in the text that have it by sets of points. I'm going to just do it more visually using graphs over here. So here's a very simple function I'm going to draw. There's my x, there's my y, and here's my function. It goes forever and ever. So that's a function, whatever it is. It's, y equal to something. Okay. We're going to talk about the domain over here. So the domain is a set of all the possible inputs. Here's x, meaning I can input anything for x. So the domain for this thing is all real numbers. X can be anything. For any x, I go to an x, I have a y, x and y. So this is one way of writing. We can talk about describing the domain in words. We could also do it in some sort of an inequality. We could also say that minus infinity is less than x is less than plus infinity. They mean the same thing. This and that are the same thing. We can also use interval notation. And you need to be well versed using all of these. Now this is where it gets a little confusing, because with interval notation it looks like the coordinates of a point. Interval notation looks like this. These parentheses do not mean the coordinates values of a point. They mean an interval on this number line, and this goes from minus infinity. Notice I'm not including infinity because it's a parentheses rather than a bracket, all the way up to positive infinity. So these are three different ways in words, using the algebraic inequality, using interval notation, and this last one is using what we call set builder. This is the mathematical way of expressing it. And you would write this. So in essence, your domain, D for domain, is equal to, we use the braces over here, that means the set of all elements x, that's my input, such that little line means such that x, and I'm going to use this epsilon, which is an element of the real numbers. You could write it like this, or you could write it also in this form. D, the domain, is equal to the set of all elements x such that minus infinity is less than x is less than infinity. Well, since it's a little shorter, I'll probably prefer to write it like that. So there are four different ways to express, if you will, the domain in words, and you need to be comfortable with all four of them. So in the textbook, it'll ask you to give all four for each of those. Okay, we did the domain. Let's take a look at the range. So now let's take a look at the range. Remember, the range is the output, so it's the y value. So for any x, I can have any y. Well, in that case, it's identical, but I just replace the x with the y. So here we have the range is all real numbers, or minus infinity is less than y. Now the range is with the y, it's the output, which is less than positive infinity. Or if I write it in interval notation, I could write it here, R for range is this set minus infinity to plus infinity. I could have put a D over here if I wanted to define my domain. Or I can use the set builder notation, so the range is the set of all elements y such that y also is a real number. So we use the Greek letter epsilon to them is a member of that set. So that's a simple example. Let's take a look at another example that you've seen. This is a simple example of a straight line that you've already seen. Take a look at another one. Here's our second example. So there's my function right here. Now my domain over here, if I can just, I can kind of write this over here if I wanted to. I could just say, y is a real number. I could kind of write this in that way. Y is a real number, all real numbers. So the domain over here, I'm going to use that simplified notation. Say the domain is that x can be any real number. Using the double R to distinguish it from the range. That means a real number as opposed to a single side on the R. Meaning, I can give you any x value and find a y. What is different here is the range. For the range, what happens? Well, the output can't go beneath the x-axis. So for the range, let's write it in set builder notation. I'll mix the two so you can kind of see different ones. The set of elements y such that y is greater than or equal to 0. It can be equal to 0 or greater than 0. It can't be negative. So that's what it is. We identify the domain and range, and you need to be comfortable doing it 4 different ways. So for the answers, they may ask you to write it in 4 different ways. And that's all it is. So we now have our domains and range when we know the graphs. And sometimes it's a little bit, harder to distinguish. This is not so bad. Hopefully you can start to see the pattern over here. Here's another example. This is a function, meaning it passes that vertical line test. The domain over here, hopefully you can see that the domain is x is any real number. I can put any number in for x and I get a value out for y. The range, however, here is that y is also any real number. I can get any value of y. Sometimes it's a repeated value. That's okay. The y can be repeated. The x cannot be repeated. So in this case, that graph is given by the domain and range defined by that. Let's take a look at one last one and then we'll go to the next topic. Let's say I have something that looks now like this. This is going to be a subtle one over here. We'll see this more later on when we start looking at it. I'm going to put a value of 1 over here. My graph is going to look something like this. It's never going to hit that value of 1. It's never going to hit that value of 1. Now, this is going to be a little bit harder. We're going to actually need the algebraic representation of that function, but I'm going to tell you what the domain and range of what I've drawn there is. It's as follows. Now, as far as x goes, it can be any number except 1, because at 1, I have no defined value. So for the domain of this, you can write it in set builder notation. It's a set of all elements x such that x is a real number, but x cannot equal to 1. I exclude that 1 value from the domain. The range is also a little subtle over here. That's the y value. So it's just, y can also be any real number, but it's subtle because what you don't really notice here is that this never touches the x-axis. So y can never equal 0. Whatever x value I put in, I will never get a value for 0 out for y. If you want to look at what this would look like, this is the y would equal to, say, I'll do it as 1 over x minus 1. That's the algebraic representation of what I've just drawn there. So we have to look at it and determine what can I put in? Anything but 1. And what do I expect out? Any number other than 0 will come out of this. I will never get 0 out of that by plugging various values of x. I can get close to it. If x gets really, really big, say 1 over a million minus 1, that's 1 over 999,999, that's a really small number. It's 0.000001. It's a very, really small amount there. Okay, so that's essentially what we have for our function and its domain and range. Let's finish up with how we're going to write this. We need a special notation now that we've defined something called a function. What is the notation attributed to functions? Well, the word starts with the letter F. So at the place to start, we're not excluded. We're going to have different letters to represent function, but the most natural way to start is to use that letter F. So now let's take a look at function notation. And this gets confusing for a lot of students. Meaning we had an equation. So here's my equation. Y is equal to, say, x squared plus 3x plus 4. Okay? Instead of writing y, I'd like to create a new notation. So I'm going to replace this y with the letter F. And now I'm going to use parentheses. These parentheses don't mean the same thing they do when you're multiplying algebraic expressions or working with them. But these parentheses just identify the input. This is not F times X. This is read as F of X. It does not mean F times X. It's just I'm replacing Y to explicitly show the input. X is the input. The F of X is the Y value, is the output. So I'd write that F of X is equal to x squared plus 3x plus 4. So that's my function notation. Now, what does it enable me to do? Well, it enables me to do some very simple things. So given that, let's turn around and do these evaluations. We can use this to give us some simple ways of doing evaluation. So for example, say I say, can you find F at 0? All this means is wherever I have an X in here, I replace it with 0. So I come over here, that's 0 squared plus 3 times 0 plus 4. Well, 0 squared is certainly 0. 3 times 0 is 0. Plus 4, so that's it. It's a very short way of evaluating. It says when x is equal to 0, y, or f of 0, is equal to 4. That's all it is. If I turn around here and put in f at, say, -1, I come over here and I evaluate. Square -1. 3 times -1 plus 4. Squaring -1 gives me a +1. +1 minus 3 is negative, in this case 2. Add that to 4, and I get 2 out. So I can put anything into my input. For example, let's try this one. This is the one that we're going to need this in the calculus to start getting used to this. F of x plus h. Oh, now we're putting the sum into my input. What does that look like when I substitute it over here? Well, wherever I have an x over here, I'm going to replace it with x plus h. So my function form, this is the function form, it takes my input, I square my input, that's what this is, input squared, plus 3 times my input, 3 times x, x is my input, plus 4. Well, my input over here is not just x, it's x plus h. So wherever I had the x, I'm going to replace it with x plus h. So that's what it looks like. Now, what I will do later on, we'll be multiplying these out and doing some simplification. But for now, we'll just leave it like that. You know, if you want in the text, you multiplying it out. Now, you can also do these other manipulations with functions. I could do, say, 2 times f of x. What does that look like? Well, it's just equal to 2 times that function f of x, which is x squared plus 3x plus 4, which is just 2x squared plus 6x plus 8. So this new notation, we can use it to do some interesting things with. Just have to get used to it. Those parentheses, it doesn't mean f times f, it's just the name. This entire thing is just another way of writing y. Instead of writing y, I write that. So I'll have you work some problems. We're going to be doing a lot more with these function notation. This is just the beginning of it, and it's easy at the beginning. We don't want to make it too complicated right away. That'll come as we progress. But let's kind of, in the end over here, review everything that we've done. So here's a summary of what we've looked at today. And I want to give you some problems to work for the homework that we'll be kind of going over on Tuesday of next week. Here's a summary. We looked at this concept of functions. Let's get a better, let's see if I can place this. Need to get another, I can do that. I need more ink. Kind of running dry over here. Hopefully it starts coming. Okay, for functions, what did we do? We defined what a function is. So we gave the definition. And then we learned how to find it. We know that it's a set of ordered pairs where the first coordinate is never repeated. We identify it graphically. So we also learned how to identify it with the vertical line test. And one thing I left out here we're going to do as well. The other thing we learned, or didn't learn, but I want to mention here, is how to define a function algebraically. So I wanted to add this thing, because as I was going in the back of my mind, I said, oh, I left that out. We can define it, through a definition. We can define it from a graph, but we can also do it algebraically. So here's an algebraic way to define if an equation in two variables represents a function algebraically. And this is done. Now, if you can uniquely, all these are equivalent. The vertical line test and the definition we gave are all equivalent. Uniquely solve the equation for y, the expression that you have, the expression that you solve for y is a function. Let me just kind of end with some examples. For example, I have y minus 3x is equal to 4. Well, I can move the 3x over, and I get y is equal to a positive 3x plus 4. I was able to solve it for y. It is a function. What about this? Y squared minus 2x plus 5 equals, or minus 5 equals 0. Okay, well, I'll try to solve this, if you will, for y. Let's move that over. So I get y squared is 2x plus 5. Now I take the square root. But remember, when I take the square root, I have to look for both the positive and negative values. So this is equal to, y is equal to plus or minus, when I take the square root of 2x plus 5. It's not unique, meaning there are two values. So for this x, I get a positive value for y and a negative. If I put in 0 for x, I get two values, plus or minus the square root of 5. So this is not a function. I can't solve it uniquely. So that's a problem. So there'll be some problems in the homework to look at, and we'll go over anything you might have difficulty with. So let me kind of give you some of the homework problems here, and I'll answer any last-minute questions that you may or may not have. Now for the homework for this, it's all about functions and the basics of function notation. Go through the problems. Also, read through the text if you're having any difficulty. Spend some time on those algebra problems as well. So here's our homework, and it's section 1.1 1 on page 9, numbers 1 through 33. Look at all of them. You can look at just the odd ones, but I have the answers for the even and the odd. So if you just want to do the odds, that's okay too. Page 1.2 on page 13, numbers 1 through 10. This is the basis of function notation. This talks about relations, functions, and the domain and ranges of them. And looking at graphs, are they functions, are they not? And looking at algebraic expressions. Are those algebraic expressions not a function like this one, or they are a function like the other one? So this is all start. If you don't understand something, I expect you to come in next time with questions. If not, then, I guess it was easy enough for you. But don't be timid. Ask the question. You're paying for the course, so make sure you understand it before we move on, because it will get a little more complicated. But that's a new idea. This new idea of functions and the function notation that we talked about over here, which is that now f of x. I remember when I first calculus, because I never had pre-calculus. I had to teach myself pre-calculus. It was in the back of the appendix of the calculus book of the course I was taking calculus. I had been out of math for a while. It was after I was in the military, I was in the Air Force, and I was just thrown in calculus, and I just taught myself. The instructor first day put that f of x up, and that confused the hell out of me, because no one ever showed me that before, having bypassed all the pre-calculus. But then I was able to figure it out, taught myself all the pre-calculus I needed, and was quite successful in it. But it was a little bit strange for me, so I understand that notation looks kind of odd, because he was throwing it up there, because all the other students in the class had pre-calculus. So I just, okay, I'll figure it out, and I did. F of x. It's not f times x, it's f of, there's my input. Plug in an input, the output is an f of x, which we call a y value. Just think of it easily. Everywhere you see a y, you can replace it with f of x. That's all it is. Not f times x, f of x, because this is my input into my function machine. The output is the f of x, which is associated to the y coordinate. Okay, any questions in the remaining minute we have left? Anyone have any questions? Yes, Matthew.
How are we supposed to see the questions?
What I can do is, if you don't get it just yet, what I'll do is I will put in the first section and some of the answers. Maybe at the end of today, or probably early tomorrow, because I have to do something this afternoon. I'll put the essentially the first portion of it online. So look at where there'll be another link I'll put there for a textbook, and you kind of look at that. Okay, we'll do that. Hopefully you get the textbook soon and everything else, and kind of work these and start getting into it right away. It's the other reason why I had put out the course outline earlier, in hopes that people might try and procure the textbook ahead of time. But I understand. Any other questions? We'll take a look at those, and then we move on. We're going to be hitting on domain and range a lot, so get used to the domain and range. And also practice. You can start by practicing and reviewing some of those algebra concepts. So if you don't get it, if you wanted to start doing something now, go to the algebra stuff that is online and make sure you're comfortable, because we're going to do a lot of algebraic manipulation. And even more so when you get to the calculus. Any other questions? Okay. Well, smile, wake up, stay healthy. We will see you on Tuesday. Remember, Monday is a holiday, so we're not going to be here on Monday. I'll stop recording now. And this recording will take